All right, welcome back. Today is Unit 7 and Unit 9, sort of combined day 2. And we're going to actually start off with a bunch of formulas that you will not find on the reference sheet on a Regents exam. There is an exponential growth decay formula on your Regents exam. I just want to point out to you that we have never used it, nor do any teacher that I've ever talked to know what that formula is for. So please don't use that formula at all. I promise it will not benefit you. Follow these formulas. Anyways, so if we are talking about an exponential growth or decay function, and it's just your basic function, we have a few different variables we need to discuss. I consider it my after amount. After a certain amount of time, how much money will I have, or how much bacteria will I have, or whatever the problem's discussing. P is usually what we consider our principal amount. So I'm going to use the space up above to tell you what these different variables are. So P is your principal amount. R is your rate, but remember, converted to a decimal. So R is your rate, but as a decimal. T is time, obviously. And you'll see a few other variables as we get into a problem. So when we get to our second formula here, we have an A, we have a P, we have an R, we have a T, but then there's this N. If you're reading an equation, it says the word compounded and then says another word after it. For example, monthly, weekly, semi-annually, daily, any of those sort of words. N is the number of compounds that happen within a year. So that's the number of compounds. So Joe deposits $150 in an account. That's his initial or principal deposit. It has an interest rate of 3.2%. As a decimal, I know this looks like it's a decimal, but that's percent. Convert it to a decimal, that would be 0.032. Compounded monthly would be 12 times a year for 5 years. So we have all the variables that we need. So A equals 151 plus 0.032 cut into 12 pieces raised to the 12 times 5. And so I would type that in my calculator. And since we're talking about money, I'm going to type that all in at once. I'm going to pretend that I just did that. $175.99 is what it ends up coming out to be, rounded to the nearest penny. Now, if they use the word compounded and then the word continuously, that is our key to use something called, what I call PERT. And this is the formula for compounded continuously. So again, we have an initial investment. The loan has an interest rate of 4.5%. So that's 0.045 for us as a rate. And compounded continuously, E, remember that stands for Euler. That is just a constant. So that's a button in our calculator. How much will she owe after 7 years? So let's find out. So we have 5,000 E to the RT, so 0.045 times 7. This one I will show you in my calculator just so I can show you where the E button is. So 5,000, and then E is in two different places. We have E right here in blue, and we have E right here in blue. Either of those E's works for me. I'm going to use this one. So second natural log, and that should put the E in my calculator there. And then I can type in the rest of the numbers here. 0.045 times 7. All right, round to the nearest penny. So it looks like I'm going to have about $6,851.30. All right. How can we use a geometric sequence? Now, this one actually is on your reference sheet. So you actually don't have to memorize this one, but it does fit into this unit pretty well. It says write an explicit formula for the following sequence. Remember, A1 is the value of the first term. R is your common ratio. You'll learn and be refreshed more on this when we get to Unit 8, which should be the next video that you watch. But AN equals 5 parentheses. Now to get from 5 to 20 and 20 to 80, we're multiplying by 4. So 4 is our common ratio. And it says using that formula, if 327,680 is an answer or a value of a term in a sequence, what is the n? What term number is that equal to? So that equal to our equation. And let's isolate and use maybe common base is drop the base. Let's see. So if I divide by 5, that gives me 65,536. I don't know 4 to what power is that. So I kind of did some guess and check. I could start with like 4 to the 6th. It's obviously too small. Then I was like 4 to the 7th, still too small. 4 to the 8th. I kind of just did get some guess and check until I got there. So 4 to the 8th power is equal to 4 to the n minus 1. Once I have common bases, I can drop the bases and solve for n. And I would say that it's the 9th term in the sequence, but we are going to fresher memory. So you could also have logged both sides. So I could have used logs too, if you wanted to. Oh, another formula that you will want to maybe memorize is the half-life formula. So the 0.5 is already incorporated into the formula for us, and that's because it's determining half, how much time it takes for a substance to cut in half. So you're observing a mystery isotope. At 1 o'clock, there's 3.5 grams, and at 9 o'clock, there is 6.2 grams. What is the half-life? So literally, there's our question right there. We don't know H. Our after amount, so after time has passed, we ended up with 6.2. That's our after amount. So I'm going to write it over here. 6.2 is our after amount. Our initial amount we'll call is the 13.5. 0.5 itself is part of the formula, so that's not going to change. And to think about going from 1 p.m. to 9 p.m., that is 8 hours that has gone by. You know, this one is not the cutest. It's not the cutest numbers to be dividing in a calculator. So if I do 6.2 divided by 13.5, it's not the most beautiful decimal. And if I hit math, enter, it really just keeps the same numbers. It just gets rid of the decimal place. So I'm just going to clean it by writing it as a fraction instead of that long decimal. Now, in this instance, I can't get common bases, drop the bases like I did on the previous question. This is where we're going to have to tap into our logging of both sides. So if you remember how to BAP, this is log base of the answer, which happens to be this fraction, equals the power. So we have log base 0.5 of this fraction equals this. We would have to cross multiply, which really ends up doing 8 divided by, and then this log kind of swaps places with that H. So that's how I'm going to type it in my calculator. I know it looks wild, but let's do it. So I have 8 divided by, or I could use alpha y equals if you prefer that, 8 divided by. And then to get that base, remember it's math, alpha math, 0.5 of 62 over 135, hit enter, and there you have it. Our half-life is about 7 hours or so, which if you think about it, kind of makes sense. If we had 13.5 and we're getting down to 6.2, that's a little bit under half, and that happened in 8 hours. So it makes sense that half of the substance would have decayed in about 7 hours. So it actually kind of makes sense. All right, moving on away from formulas and into expanding and condensing logs. Biggest thing about logs is if you have multiplication, that's the same thing as separating them with a plus sign. You have division, that's the same thing as separating with subtraction. And if you have an exponent, that's the same thing as a coefficient. So it sort of like loops back and up and forward. All right, so in this particular example, log of x times z squared, if I separate that, multiplication becomes addition. And this exponent of a 2 would pop out in front of just the log of z. Because that is the exponent on the z only. All right, in this case, we have 2 multiplied by x, and then that whole thing is being divided by y. So if I was to split this apart, and I might run out of a little bit of space, log of 2 plus log of x. And then because this is divided by y, I'm going to subtract log of y. See how I kind of ran out of space? You see what I mean? All right, we got lots of stuff going on here. 4 times x times the square root of m. So let's think about that. How could I write the square root of m as an exponent? Well, hopefully all of you are thinking of it like this. A square root is the same thing as having an exponent of a 1/2. So we have log of 4 plus log of x plus, and then 1/2 log of m. So all of those are being multiplied, which is now when I separate them, they all become plus signs. Now this fourth example is already in expanded form, because if you notice, the word natural log is written multiple times. So you kind of have to keep track and order of what is happening. So like here, we have natural log of y plus natural log of z. That is just telling me that that is y times z. But there's a 2 in front of it. I'll get to that in a second. This 3 is only going to impact the x of the first log. So this is really natural log of x to the 3rd power. There's still a subtraction between them. Now remember, subtraction is division. So when you're done writing your final answer, the word natural log, or ln, should only be written 1 time. So x to the 3rd is our numerator, and then this 2 has to pop up and be an exponent for both the y and the z. Both are being squared. So notice how I wrote natural log only once. All right, flipping it over. Probably one of the most difficult topics of our exponentials unit is mindful manipulations. And there's 3 major types of mindful manipulations. Option 1 is when you are given the annual growth model and you have to balance it to expand it one way or another. So if I give you this annual growth model, this means that 20% is telling me that because t is in years, once a year, it grows 20%. But what if I was like, okay, well, that's how much it grows in a year, but I need my business to tell me how much my business is growing in a month. How could I take a year and convert it to a month? Well, a month happens 12 times per year. So if I slap a 12 in front of t, I need to balance it by bringing in a 1/12, meaning one of the 12 months out of the year. So in my calculator, I would be doing 1.2 raised to the 1/12. And that should hopefully convert to a monthly rate. So that would be about 1.5% growth per month. So that's the kind that I consider like balancing if you go from a yearly to a different model. If this was like weekly, it would be 52 out here and 1/52 in here. If it was weekly, oh no, I just said weekly. Quarterly, 4 1/4. That's how you would balance it. Okay, well, what else is there? Well, what if the balancing was already like pre-done for me and I want to go backwards back into a yearly model? This for me is the easiest of them all. If it's already in terms of something else, all you kind of have to do is like reabsorb. This 52 gets like reabsorbed back into the parentheses so that now your outside exponent is representing once per year instead of multiple times per year. Now, this might not be the best example in the whole wide world, because if I do the 1.05 to the 52nd power, it becomes this ginormous number. Now I know you're like, what? It's only 12. That's not that big. But 12 on the inside of parentheses like that is actually really large. So this probably wouldn't be the best example in the whole wide world. So that would be growing at like 1,164% per year, which is a huge amount. So that's a weird example. The third and final type of mindful manipulations is what if your exponent is not in terms of years, but it's in terms of something else. So if you look at this example, it says t is months. We're so often assuming usually that t is years. When I read 1/6t, that 1/6 means once every 6. And then because t is measured months, it's once every 6 months instead of once every 6 years. The only conversion that they'll really ever ask you is, again, sort of the absorbing situation where you take that 1/6 you bring it on the inside, and now because this is a 1t, and that t is representing months, I can now figure out what 1 month is worth. So again, this is that absorption sort of. So 1.3 raised to the 1/6 power. Let's see what that is. Okay, so this particular, whatever we're talking about, converting that would be about 4.46% growth per month, because I was able to absorb it and create that outside to be just 1t. And we'll do an example of that a little bit later in the video. Solving exponential equations. We kind of already had a taste of this too on the previous page. Solving exponential equations using common bases, not using logs. So we want to get both bases the same. Usually we want to make the bases smaller. A common mistake is they're like, oh, 9 and 27, I'll just multiply this side by 3. That's not how exponents work. What you need to do is actually rewrite the 9 as 3 squared. But since there's already an exponent up there, you're going to multiply the old and the new together. So same kind of idea here. How can I turn a 27 into a base 3? Well, 3 to the 3rd power is 27. And since there's already an exponent up there, I'm going to multiply the old and the new together. Now that I have common bases, I can drop the bases, distribute maybe, save myself a rewrite, and I can get to my answer pretty quickly. So next example, same idea. You want to bring it to the smallest base probably. This one's already 5. I can't go much smaller, but luckily the other two can be rewritten in terms of 5. So 25, remember, is 5 squared, and 125 is 5 cubed, and there's already an x up there, so I'm going to multiply them. And before I go dropping bases here, if I wrote x squared multiplied by x to the 3rd, hopefully you all say x to the 5th. What did I just do with the 2 and the 3? When I multiply, I add my exponents. So when I multiply, I have to add my exponents. So when I drop my bases, I have 2x minus 1 plus 2 is equal to 3x. That is 2x plus 1 is equal to 3x. And you can easily see our answer now is just 1. Sweet. Not flipping over. Commonly mistaken with, ooh, that's a little shaky, is solving fractional equations because it looks like it's the same thing, but it's not. First thing you want to do, because since this is really a power equation, is divide and isolate. So I'm going to isolate my variable to the best of my abilities. That's about as isolated as I can get it. Now, since there's no way for me to get common bases, drop the base, because this is a base x. What I need to do is raise it, both sides, to the reciprocal power. The reciprocal power of -1/3 is -3/1. All right, that gets rid of that. Now, 3 to the -3, I could do that all by hand because I could say, okay, well, negative exponents make fractions, and 3 to the 3rd power is 27. Well, watch, I'm going to show you the exact same thing. 3 raised to the -3rd power. Enter. You're like, what? That's not what you were just saying. But if it hit math, enter, enter, it does. It's 1/27. All right, let's try another one. Subtract 9, subtract 9. 16. All right. I'm about to raise both sides to the reciprocal power again. However, when I raise both sides to the reciprocal power, so that would be -3/4 and -3/4. Now remember, I'm raising it to the reciprocal power, not multiplying it by. If the base of your reciprocal is even, you need to put a plus or minus in front of your answer. It's basically like when we square root something squared, we put a plus or minus. You're essentially getting an even denominator in your exponent, and that creates two possible solutions. Your calculator, unfortunately, so 16 raised to the -3/4, if I could type it in correctly, is only going to give you one answer. You have to be smarter than your calculator and know that there's a plus or minus 1/8. Now, look at this. This is a nice section because I can just go, ooh, we already did it. I copy pasted it too many times. So moving on to solving logs. We've already sort of dabbled in this a little bit. There's two different methods we taught you this year. Lassoing, that's if there's a log only on one side of the equal sign. If there are logs on both sides, that one's even better because we could just drop the base. So let's lasso this first one up because our log is as isolated as possible. What that means is there's nothing out front that I need to divide to the other side, and there's nothing outside of what I'm taking a log of that I would have to add or subtract to the other side. So I can go right ahead and lasso 2 to the 5th power. So 2 to the 5th power is 32, and that equals the 5x plus 7. When you lasso a log, it goes away. There's no more log in the word. So no more word, no more log. All the logs are gone. And we can solve very easily. So if we want to practice that again, remember lasso a log. So you take your base, whoop, loop it up, 5 squared. Not 5 times 2, 5 squared is 25. Simple solving from there. Your answer for a log equation like this, as long as your answer does not create a negative in what you're taking a log of or in the base of it, your answer should work fine. The only way you'd reject an answer is if you plugged in that 5 and for some reason that created a negative result on the inside of the log, then it would reject. Now here we are, logs on both sides, they're the same base log and they're as condensed as they can be. I can literally just drop my logs. And solve for x. If the logs aren't condensed, for example, number 4, see how there's 2 logs on one side equal another to another log? I need to combine these together using my condensing log rules that I crossed off on this page, but we did on the other page. Remember, a plus sign is the same thing as multiplication. So this is really log of 2 times x plus 3. Now that's a lot of parentheses. So if you're able to do that distributing right away, feel free to do that. I'm going to drop my logs at the same time. So 2 times x plus 6 equals 14. Subtract that 6 over, and I can easily get my answer. All right, last page. Well, what if we have to go the other way? Because remember, logs and exponentials are inverses of one another. So we just solved logs. Sorry about my dog. We just solved logs. Now we're going to solve an exponential function by using logs. So this is what I call BAP. I'm pretty sure your teachers do as well. BAP stands for a base answer. Well, that's not how you spell answer. And then power. So first what we need to do is get this in proper form. So as isolated as possible. When we say base, the log base, that little tiny number, and the base of your exponential, which in this is a 4, need to match. So log base 4, this is our base. Of the answer, what that means is what comes after the equal sign. In this case, it's a 21. So 21 is our answer. And then it equals the power. Obviously the power, that's the easiest part to spot. That's the x. So it's log base answer power. We call it BAP, not because it looks like BAP here. It looks like BPA here. This is your base, your answer, your power. And then remember math, alpha, math. Math, alpha, math is the shortcut to get to the log base. So if you want to go the long route, it's math and then scroll up from the bottom, but I'm just going to do math, alpha, math, and boo, it goes right to it. 4, 21, and hit enter. And normally there'd be some sort of rounding directions of some sort. 196, whatever, dot, dot, dot. Now let's do it again. Isolate to the best of your abilities. I have it isolated. Now let's BAP it. So log base answer power, and then I type this in my calculator. When I type that in my calculator, I get about 1.113 dot, 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 dot. And last but not least, remember E is one of our exponential functions. The inverse of E is natural log. You don't have to write the E in a natural log. It's assumed, hence the name natural log. So natural log base E, you don't have to write it, of the answer, which is 14, equals the power. Now this one has one extra little step in there, because not only do we have to find natural log of 14, which by the way, natural log has its own button right there. So if I press natural log of 14, I get this little decimal. So 2.639 dot, 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 dot. Subtract that 2 over. And that would be our answer, because we had to solve for x still. All right, so let's just do a couple application problems here, and then we're done. Use your log properties to determine the transformations on g of x. So our log properties are expanding properties that we practiced already. Here's our equation over here. There's a lot of stuff happening in the inside there. We have 4 times x to the third. So if I was to maybe do our first expansion, that would be log base 2 of 4 plus log base 2 of x to the third. Now that's not as expanded and cleaned up as I could potentially make it. First of all, log base 2 of 4 is really saying 2 to the what power is 4. Now we know that answer, but we can confirm it here that log base 2 of 4 is 2. So this is really 2 plus, and then this 3 can pop out in front of its log here. And what we just did was we expanded this, and now we can determine transformations. If there's something adding or subtracting in front or at the end, really, that's going to be a vertical, or that's going to be a shift. In this case, up 2. If there's something out front where this A is, which in this case we have a 3, that's going to be a vertical stretch. What we don't have seen here is if there's something shifted on the inside with the X, which we don't have, that would be shifting it left or right. And that would be telling us whatever our asymptote is. All right, number 2. Given the equation represents the growth in Matt's bank over the term T years, what would be the weekly rate of growth? Great. Okay, so they're giving us that T is years. This current exponent means once per year because it's a 1T. I want to turn it into a week. Well, there are 52 weeks in a year. So what I need to do is balance this equation and modify it. I'm going to leave some space. A week, there are 52 times in a year that weeks happen, but I want to know how much it's growing in one of those. So I need to balance it by saying, okay, I just want 1/52nd of this. This should help tell me what my rate for 1 week is. So let's find out. So 1.25 raised to the 1/52nd, 1.0043. If I convert that, so -1 times 100, converted to a percent, it would only be growing about 0.43% per week. Growth per week is how much that would be growing based on that equation. All right, number 3, the Richter scale measures the magnitude of an earthquake is defined by the following formula. E is energy released by the quake. In 2011, there was an earthquake in New Zealand that measured 6.3 on the Richter scale. So that's going to be our R value here. In scientific notation, rounded to 3 decimal places, how much energy was released? So that E is what we're going to be trying to solve for. All right, so let's plug and chug and let's see what we can solve here. So I'm going to substitute in our 6.3. Ooh, we got a lot of solving to do on this one. So we have to subtract the 1.46 over. Then it looks like we're gonna have to divide by this 0.67. I'll squeeze that in before I have to rewrite it again. So divide that out. So I get 7.2238 equals log 0.37 e. Let me quickly type that in there so I have that number, the full number saved. Okay, so we have this number. I need to solve. It's a log equation. We just practiced this on the last page. We want to lasso it, but if there's no base written, remember a log's invisible base, if there's nothing written, is a 10. So this is 10 raised to that power. So I'm going to save that answer in my calculator, 10 raised, and then I'm going to copy paste and just kind of drag that in. Ooh, that's a long number. I'm going to write the whole thing. Write the whole thing. So I did 10 to that equals 0.37 e. So divide this answer by 0.37. That is a big number, which I guess you would expect if an earthquake's going off, that it would release a lot of energy. But that's not our final answer, because this does say, write your answer in scientific notation. That is a throwback. Scientific notation is like when you have times 10 to the. So let's count. It says 3 decimal places. So scientific notation always starts as if the decimal place was here. So let's see how many swings that is. 1, 2, 3, 4, 5, 6, 7. So we are going to have times 10 to the 7th, seventh power. 4.52, and then this 6 is going to round up that 5. So 526 times 10 to the 7th power would be our answer in scientific notation. Last but not least is a little bit of calculator work. Equations represent population, and X is representing years after the year 2000. We have event A that starts with 3,500 people and it's growing at 15% per year. Event B has 15,000 people to start, but unfortunately it's decaying over here every year. When will they have the same population? I'm going to use my calculator. We are not going to solve this one algebraically. So what I would like you to do is type in, oh, I don't know why I cleared that out. I already had it in there. Type in your equations in Y1 and Y2, like I have here. And let's think about this. We have one that's starting at 3,500 and going up. We have one that's starting at 15,000 and going down. If I go to my table of values, what I notice is we want to know when they're the same, right? If I look at my calculator here. Let's see. There we go. Okay, so 3,500, 1,500. This one's going down as this one's going up. Something happens somewhere around 3 to 4 because we have 5,000 going to 6,000, and this is going from 6,000 going to 5,000. They're crossing somewhere between 3 and 4. So I need to adjust my window. So let me jot this down. I checked my table. I'm like, something's going on between 3 and 4. I'm going to change my window to go from 0 to 10 in the X values. And I'm going to make my Y values go from 0 to 15,000 because I'm like, you know what? This one starts at 15,000. I know I'm going to see everything I need to see if I go up to that. So window, 0 to 10 in the X's, 0 to 15,000 in the Y's. Pick graph for me. Here's what I see. I'm going to draw myself a little sketch. There's the event that's going up. There's the event that's going down. They clearly are crossing in the middle, and I want to find out when they equal each other. So second trace, option number 5, move that blinky spider if you want, but it's the only intersection point, so hit 1, 2, 3. Beep, beep. That intersection is at 3.6279, comma, 5811.3862, something like that. This does not say in how many years. This says when. Since X is representing the years after to the year 2000, here's your X. So in the year 2000 plus 3.6, that would be in the year of 2003. We'd be probably like in the 7th month of the year, a little over halfway, but somewhere in the year of 2003, they will have the same population. Now, part B says, what will the population be that year to the nearest person? So obviously to the nearest person, 0.3 will not round up this number. The Y is how many people. So 5,811 people would have attended or been the population that year for these two events. Hope that all makes sense. See you next time.